All right, we're going to continue on with our AP Physics 1 course review. The next topic is momentum. So momentum is, a vector product, as in it's the product of the mass of an object and its velocity. And so momentum has direction, and it's always in the same direction as your velocity. In magnitude, if that's all that's needed for a certain calculation or problem, it would be the mass times whatever the actual speed is. Speed is the magnitude of the velocity, which doesn't include direction. The units for it would be whatever the combination of units for m and v are. So kilograms for mass, velocity, meters per second. So the units are kilograms times meters per second. Typically, problems in the AP exam are in reference to collisions. So there's different kinds of collisions. One common kind that may show up is they might call it block A, is moving to the right, and it can collide with block B, which has an initial velocity of 0. There are two common examples. One is called a perfectly elastic collision. To have an elastic collision means carts do not stick together. And it also indicates that the kinetic energy is conserved, which means that however much kinetic energy block A has as it flies into this collision, block B, well, after the collision, block B will be moving. Block A will actually stop after it collides with block B. And block B will move off with the same exact velocity that block A originally had. That's commonly seen with cue balls. When you hit a cue ball straight into another ball, this ball will just stop, and this ball all of a sudden shoots off. And that would be considered, in the real world, there is always some energy loss. When the balls actually hit, they warp a little bit and change in their shape, produces a little bit of heat. In physics, we like to talk about the most idealized scenario, and a perfectly elastic collision is the most idealized scenario that never actually occurs in our real world, because specifically because one of the parts of this definition for perfectly elastic is that the total energy coming into the collision is equivalent to the total energy going out of the collision. In our real world, when we do the cue ball example like I just described, if the cue ball was coming in with 5 joules of kinetic energy, this ball might only actually leave with 4 joules of kinetic energy, and this one still would stop, but you would have lost some energy, 1 joule in this example, to heat. In a perfectly elastic collision, kinetic energy would, in fact, if we could actually make it happen in our real world, kinetic energy would be conserved, which means there would be no energy lost to heat, and the total energy, kinetic energy coming into the collision would be equivalent or equal to the total kinetic energy of the objects after. So know that in perfectly elastic collisions, this is the case. The first ball object would collide with the second object. The first object would stop completely, transfer all of its momentum over to block B, and block B would move off. Block B would start moving in this direction with a velocity that's equal to whatever this original velocity was. It would be a perfect transfer of momentum. If this person came in with 10 units of momentum, just say 10U, then this guy will move off with 10 units of momentum. That's called a perfectly elastic collision. The other kind that turns up fairly often is what's called a inelastic collision. So inelastic collision means that the objects stick together. Kinetic energy is not conserved. and this does happen in our real world. Some energy is lost as heat. In the collision. But in AP problems that are typically a flat surface and a road, or a flat surface like a road with a block, you can think of it as a card flying along and collides with another block, call it A and B. The one that often shows up is that the initial velocity of B is 0. This guy has some initial velocity to the right. This would be the before collision. And then after collision, they've stuck together, and they've both joined, and they're both moving afterwards with some final velocity and momentum. This would be after collision. So the quickest way to, often what's asked would be, what is final velocity of these two blocks stuck together? And you just have to recognize that an important part of the momentum unit is called the conservation of momentum. That the total momentum prior to any collision as a vector quantity is equal to the total momentum of all the moving objects after the collision as a vector quantity. So that's to say that you can't actually just create momentum, and you can't from nothing, and you can't take momentum that already originally exists and just completely make it vanish from the universe. That during collisions, there's an exchange of momentum, and that when one object transfers some momentum to the other object, that receiving object is gaining momentum, and the person that ran into that object is losing momentum. And specifically, the conservation of momentum is stating that those are equal. So that if running along and smash into some other person, and you have realized that you lost 5 units of momentum, then that other person will gain exactly 5 units of momentum. And that's known as the conservation of momentum. And typically that's written as the sum of momentum, I means before a collision, is equal to the sum of the momentum after the collision. So we can apply that. We can apply that to this particular case, this particular problem, to answer a very common question in AP exams, which is, what is the final velocity of these two blocks that are moving now as a system stuck together? Let me erase some space, maybe right here. So what you would say, or what you would do, is recognize that the momentum coming into this collision is just the momentum of object A, this guy right here. Remembering that this guy has no momentum because he has no velocity. And momentum, again, is mass times velocity. So if your velocity is 0, you've got no momentum. And so that rightward momentum of object A equal to the momentum afterwards as they slide to the right of both objects, A plus B. Both objects, this will be F, because F means after the collision of A plus B. And so all you really have to do is just sub in the mass of block A times the initial velocity of block A, and for that is equal to, now since they're stuck together, both of their masses are being combined, and they're acting now as one unit with a total mass of MA plus MB. So since momentum, again, is mass times velocity, our mass term has to combine both masses times some final velocity of A plus B. And so if this is what you were solving for, you would just divide over. So you'd end up with your solution. The final velocity of both blocks stuck together is equal to the momentum of the initial block that was moving divided by the sum of their momentums, MA plus MB. And So it's important to recognize, even though there's an equation there for you, to use to make calculation, that the total momentum of original block moving is the same value as the total momentum of them moving together. And so if this original guy's momentum was 5 units of momentum, then they also have 5 units of momentum. And so since when they stick together, their mass is going up, then they can't possibly achieve the same momentum as their block A originally had, 5 units. If mass is going up, the velocity must go down. They must be slowing. There must be some slowing effect that occurs during the collision, and we know that. Block A running into block B should cause block A to slow down. So if, let's say, for example, this was block A, and let's just say his mass is 2 kilograms, and let's say his velocity initially is 3 meters per second, then his original momentum in terms of units would be 6. So that means if he were to actually collide now with another object and stick to another object, and they're now going to move to the right, they also have to have 6 units of momentum. If object B here has a mass of, let's say the same, 2 kilograms, then the total mass is doubling. It's going from a moving object that has 2 kilograms to a moving object that now has 2 plus 2, which is 4 kilograms, right? And so the mass is doubling, and therefore the velocity is going to drop. In fact, it should be half, right? And so what you'd really be saying is, well, if their combined momentum, A plus B, has to be still 6 units, and we know their momentum is now 4, because it's 2 plus 2, what velocity must they be moving at? Because this is like M and this is like V, so that their total momentum is still 6, because the original guy had 6. And so if you were to divide it out, you'd see velocity equals 6 over 4, which simplified is 3 over 2, which simplified is 1.5 meters per second. So specifically, the pattern is showing that the original guy, remember, was moving at 3 meters per second. And so since the moving object doubled its mass from 2 to 4, the velocity is cut in half from 3 to 1.5 meters per second of velocity, so that the total momentum that originally came into this collision of 6 is equal to the total momentum coming out of the collision, which is also 6. Okay, moving on. The other main idea that I consider to be a major part of the unit is called impulse. So impulse is defined as the product of force and time of duration that the force is acting. So in my example of those 2 blocks colliding, there's some amount of time that the collision is occurring before they're just moving off smoothly at a constant speed. It's the acceleration period. It's, when that first car runs into the second car, the first car is slowing, speed is dropping, it's decelerating. The second car is accelerating, speeding up. And that might only happen over half of a second. And then after that half a second is over, both cars are now moving at a nice constant speed away from that accident. Delta T is the time duration of collision. And F is the force that they both feel, because if this guy feels a force, if block B feels a force to the right as block A runs into block B, then Newton's third law says block A will feel also a force to the left of equal magnitude, right? Newton's law says all forces are always equal when one object pushes on another object. So those 2 objects feel the same exact collision force, and this would be the collision force here. It turns out that this quantity is equal to the change of momentum of either object, because both of their changes in momentum are equal. It has to be. That's the conservation law of momentum. So remember that if you're moving along with 10 units of momentum and slam into somebody and you give up 5 units of your momentum, they'll now move away because that person you ran into was stationary originally, had no original momentum. And again, you're moving along with 10 units of momentum. Boom, you hit them, you give up 5 units of momentum. They're going to move away with 5 units of momentum. You're going to have only 5 left now because you gave up 5 of yours. So what is their change in momentum? They're moving away with 5. And you have reduced your momentum from 10 down to 5, and you have also lost 5. So that object that you ran into, delta P is 5. And for you, delta P is -5. So in magnitude, delta P is always the same for either object, but opposite in sign, because when one gains momentum, the other loses the same amount of momentum. And that comes just from taking Newton's law, F equals ma, and developing it by writing delta V over delta T is the definition of A, and then pulling apart the numerator and saying, oh, m delta V, that's a change in momentum, because momentum is just m times v. So a delta V would correspond to a delta P. And so you rewrite this, you can rewrite what I've written here by taking the numerator out, m delta V, and just putting delta P in its place. That's actually how Newton presented it to the world in the 1600s in his book Principia Mathematica. But he used calculus, so he wrote dp dt, but it's the same idea. And it's showing that the net force is equal to the rate at which your momentum changes. So if you deliver a much stronger net force to something, its momentum will change at a much quicker rate. Or if you reduce the net force acting on something, its momentum will change at a slower rate, which sort of makes sense. But the point is that when you take what I have now is F net equals delta P over delta T, and you multiply both sides by delta T, these cancel, and you get what we have here known as the impulse momentum theory. This quantity here is defined as impulse. It's how much force is acting during a collision multiplied by how long the collision is lasting, the duration of time of the collision. And that quantity is equivalent to the momentum that both objects experience while the collision is occurring. So if they gave you information about time duration, they tell you delta T is some number. They might say is 3, let's say, milliseconds, which would be 0.003 seconds. And they tell you how much force the object experienced during a collision, let's say 10 newtons, then it's straightforward to just multiply F and delta T, and you would get delta T, as I said, was 3 milliseconds. And then the force that was causing this, maybe I'll make it a larger force. Let's say it was 1,000 newtons of force, so a very strong accident, lots of force in there. Then force would be plugged in. Delta T would go in as 0.003. And when you multiply that out, you would get 3, right? So that means the impulse would be 3 units. And the units for impulse, again, are always a combination of whatever the equation units are. So it would be, not meters. It would be the unit of newtons for force and the unit of seconds for time. And so it would be 3 newton seconds. And that would be how much impulse occurred in this accident. How much did one of the cars feel in the accident for impulse? 3 units. How much did the other car feel? Also 3 units. Both objects colliding have to feel the same impulse, because the time of the collision, delta T, is the same for both objects in the collision. And due to Newton's third law, they're both going to feel the exact same force during the collision. And therefore, since the force is the same for both, and the time duration of the collision is the same for both, the impulse has to be the same for both, but opposite in sign. So if you run into somebody, you're running along and you smash into somebody, and you deliver 3 units of impulse to them, that plus 3 units of impulse will speed them up. But you'll be receiving -3 units of impulse, which will slow you down. Had someone said, what change of momentum does that cause in the person you run into? Well, now you'd end up using this right side of this and saying, oh, I can calculate their change in momentum if I know their impulse. Yes, you'd say their change in momentum is now 3, because you calculated that on the left side of the equation by doing impulse. And then you would just simply reference whatever their mass is times delta V is equal to 3. And if they gave you what the mass was, let's say they said the mass of the object was 2 kilograms, you would just stick that number in here. 2 times delta V equals 3. And then you could solve for delta V. Looks like it came out as 2/3. And remember, delta is always a final minus an initial, V final minus V initial. In a lot of problems, the object that's getting collided into, the object that's sitting there, the target object, is just sitting there. So the initial velocity is 0. So delta V would just be whatever your final velocity is, because minus your original velocity of 0 is just. And so that, in my example, you would have concluded that the final velocity of the object that got slammed into, the one that's now moving away from the collision, is now 0.66 meters per second. Sorry, that's so small in there. But that's the concept behind it. Impulse and momentum relate to each other through Newton's second law, as I derived for you on the bottom right. The quantity helps you often determine how much change in momentum you should expect to see in one of the objects that are in a collision or the other object. Notice they won't both move off, their delta V's will be different. If a very giant truck, like a Mack truck, collides into a stationary Volkswagen W, the change in velocity of the Mack truck is going to be very, very small. It'll just barrel right through the VW. So if it's moving along at 50 miles per hour, after slamming into the VW, now it's moving 48 miles per hour, like a train, running into a car. That on a track, the train's velocity is going to change by a very, very small amount because its mass is so huge. While the VW is going to have a huge change in velocity because its mass is so small. So it's not that both objects experience the same change in velocity. It's that both objects experience the same change in momentum because of the conservation of momentum theory. And both objects also, giant like a train and small like a car, experience the same force for the same time duration and the same change in momentum. But the velocity change depends on the mass. Okay, so lastly, we can show that a little bit about graphs. And so since we just had the idea that the net force is equal to delta P over delta T, that means that if you have a momentum graph versus a time graph for a collision, if you have some sort of data, let's say that looks like this, the slope of this graph is the force, because this is, and any delta over any delta is a slope, right? It's a rise over a run, delta over delta. It's a slope, it's a rate. And so if you took any 2 points on this graph, this bit would be delta P, this bit would be delta T, and if you did if you figured out a slope, which I'm certainly not going to teach how to do slope calculations right now, but if you did that slope calculation, you get some number. In my graph, let's say it came out as number 5, and you're staring at it saying, what does that represent? It represents the net force in newtons during that collision. So the slope of this, in my illustration here, would be 5. Right. That, more or less, is a quick review of momentum. I think I'm trying to just puzzle on if there's any last things I want to comment on. Nope, I think that's it. All right, the next one coming up is going to be on energy. Hope you found that useful.